Hello everyone, and welcome to this video on evaluating general transformations. Alright, and these are transformations between two vector spaces. In prior videos we had been looking at transformations between two Euclidean vector spaces, right? So from like R2 to R3, R3 to itself, R4, R5, etc. In this video we're going to come across transformations from other vector spaces, between other vector spaces, including the Euclidean vector spaces. So we have those vector spaces of polynomials of degree n or less, the vector space of m by n matrices, right? Under the standard operations, of course, is understood if I don't say it. And over a specific field of scalars, where the typical field used for the set of scalars is going to be the real numbers. So in this video I will be defining what a transformation is and going over some of the terminology that I went over in a prior video when I was talking about transformations between Euclidean spaces. So if you'd like to go back and look at those videos on the using the terminology for transformations, please do. And then after, I'm going to go over just several examples where I have transformations between vector spaces, and I'll be evaluating them, plugging certain inputs in and getting certain outputs. Okay. So my first page, just defining a transformation in general. Okay, so a transformation between two vector spaces, say the vector spaces are set V and W, denoted as, you have the name of the transformation, which, again, usually I'll use the letter T for a transformation, but you can call it whatever you want. So I have transformation T here between vector spaces V and W, or it's the transformation from V to W, you could say. So a transformation T between vector spaces V and W is a rule that assigns each element of the vector space V to an element of vector space W. So it's like it's like a more general notion of a function, right, that you're probably familiar with in pre-calculus, algebra class, whatever. Alright, now in the notation here, the set where all the inputs are coming from, V, is called the domain of the transformation, or the domain of T. The set where all the outputs are coming from, W, is called the codomain of T. Now don't think that everything in W is an output. That's not always the case. Again, if you go back and watch my videos on transformations between Euclidean vector spaces, you saw some examples where the codomain didn't have all of the outputs. All the outputs were in there, but not everything in there is an output, right? So not every element of W has to be an output of the function, or of the transformation T. Right. So yeah, don't confuse codomain with range, right? Here's the range. The range of T is all of the vectors T of V, right? And these would be vectors in W, right? These, if I plug a vector V, right, from vector space V, if I plug a vector from the domain into the rule, into the transformation, it'll give me a vector in W, right? So T of V here belongs to W. And it's all the vectors belonging to W such that the input vector was from the domain, right? So it's just a set of all the outputs, all the actual outputs that are actually mapped to by the transformation T. That's the range. So one huge thing to point out here is that the range of T is going to be a subset of the codomain of T, right? So that means every value of the range is in the codomain, but not necessarily every value of the codomain is in the range. They might be equal, right? You got the little half equal sign. They might be the same set sometimes, but not always. All right, sometimes the range of T is a proper subset of the codomain of T, meaning that every element of the range is in the codomain, but not the other way around. Okay. Then some other terminology that came up, when we were talking about Euclidean transformations between Euclidean spaces. If we plug in V, plug in an input V to the transformation T and get output W, and this is from vector space W, the codomain, we would then say that W is the image of V. All right, I guess I should add to that. I would say W is the image of V under T, under transformation T. And V then, V, the input, is n element in the pre-image of W under T. All right, because remember, again, going back to our transformations between Euclidean spaces, the pre-image of a certain vector from the codomain, right? Say the pre-image of W, where W is from the codomain. The pre-image of a vector from the codomain is all the vectors of the domain that have W as an image. Right? It's all the inputs that I could plug into the rule and get the output of W. So the pre-image of a particular output or the pre-image of a particular vector in the codomain might have one element in it, only one thing maps to it, might have 2 elements, 3 elements, might have infinitely many or no elements at all. It might be the empty set. So using this terminology, you might also call the range, I'm not going to write this, I'm just going to say it. You could also say that the range is all the elements of W that have a non-empty pre-image. If you use the terminology of pre-image. Alright, so again, I'm not going to go too much in depth here. Alright, I've brought these terms up before in prior videos on terminology for transformations. Alright, so now the rest of the video, I'm just going to go over some examples of transformations between some vector spaces. Alright. And evaluating them, for finding certain, plugging in certain inputs, getting certain outputs, and so on. All right. Okay. So here I have transformation T from P2 to R. All right. So remember, this is the set of all polynomials of degree 2 or less. Hopefully you're familiar with this notation. And this is the set of the real numbers, right? And again, under standard operations, right? The standard operations for P2, the standard operations for R. And here's how the rule works. My input, again, my input, T of the input vector here is a polynomial of degree 2 or less. And every polynomial input belongs to P2, right? Every polynomial of degree 2 or less looks like this. We have a0 plus a1x plus a2x squared, where a0, a1, and a2, right off to the side here, belong to some field, right? But typically that field will just be the real numbers, right? So we'll just be using the real numbers as the field of scalars in most of these, right? And there's my input, and the output is a definite integral, the definite integral of this polynomial from 0 to 1. And remember, when you take the definite integral over a specific interval, you get just a real number back, right? That's why my codomain here is the real numbers. So my output here belongs to the reals. Right. So let's, play around here. I'll just practice evaluating this for certain inputs. So let's find, say, T of x. There's a polynomial of degree 2 or less, 1x. Right? And when I plug this in to this rule, it just says t of x is just the integral from 0 to 1 of x of that polynomial with respect to x. Now hopefully you know, remember how this works. This is, antiderivative here, 1/2 x squared evaluated from 0 to 1. I plug in 1, I plug in 0, I subtract them. That would be 1/2. Alright, so my output here, and again, see, that's a real number. My output is 1/2. So what we would say, so using some of the terminology here, 1/2 is the image of x under t. You could also say that x belongs to, is an element of, the pre-image of 1/2. Under t. Now remember, this isn't the only polynomial whose integral from 0 to 1 would be a half. Right? There are plenty of other polynomials when you integrate from 0 to 1. There are plenty of other polynomials of degree 2 or less that when you integrate from 0 to 1 would give you a half. So this is just one element of the pre-image of a half. There are, the polynomial 1/2. Right? 1/2 would also be in the pre-image of 1/2, right? So don't think that just because this gives me an output of a half that this is the only thing in the pre-image of a half. So the output is the image of the input, all right, and the input is just one of the elements. Maybe it's the only one, but it's just, you can only say for certain that it's one of the elements of the pre-image of the output. Also, 1/2 would belong to the range of t, right? Because it is an output. 1/2 is an element of the range of t, and all sorts of things I can say here. Okay. All right. Let me plug in something else. Right. So again, my input's coming from P2, some polynomial of degree 2 or less, and my output is coming from R. Right. So how about t of 1 plus x? How about 1 plus x squared? There we go, x squared plus 1 plus x squared, however you write it. That is a polynomial of degree 2 or less. That's from the domain. And according to this, how do I find the output or the image of 1 plus x squared? It's just the integral from 0 to 1 of 1 plus x squared, of the polynomial, the same polynomial itself, dx. All right, so again, don't forget how this goes, calculus people, right? X plus 1/3 x cubed, right? An antiderivative evaluated from 0 to 1. I plug in 1, I subtract 0. That'd just be 1 1/3, 4/3, right? You can use a calculator if you want. I don't really care right now. All right, just evaluate. So yeah, so the value of t at 1 plus x squared is 4/3, meaning that 4/3, right, is again the image of 1 plus x squared. And 1 plus x squared is just one element, right, belongs to, is an element of the pre-image of 4/3. Right, again, that's not the only polynomial of degree 2 or less whose integral from 0 to 1 would be 4/3, but it is one of them. And 4/3, right, 4/3 belongs to the range of t, right? And so on, right? And just based on the words I put up earlier, these are really the only things I got, right? All right, so again, just a few things you can say when you say that t of 1 plus x squared equals 4/3. All right, and then you know, t of 0 would be 0, and you know, t of 1 would be 1. Whatever, you can plug in all sorts of stuff here. Again, my input is any polynomial degree 2 or less, and my output is simply the number I get when I take the definite integral from 0 to 1 of that polynomial. Great. All right, so that's one example. So now you're seeing some rules here. You're seeing some transformations where the vector spaces aren't the Euclidean vector spaces. So here's another one. I have a transformation here. Now this is the set of 2 by 3 matrices with real entries, real number entries. And the codomain over here is P1, right? Remember P2, that was the set of all polynomials of degree 2 or less. This is the set of all polynomials of degree 1 or less. Alright, so here's the rule. See, my input is from this R 2 by 3, right? Then my input is a 2 by 3 matrix with real entries. And my output, you see, is some constant plus some number times x, right? This is a polynomial of degree 1 or less. Right? Every polynomial of degree 1 or less can be written this way as a constant plus a number times x to the first. So this tells me how to output stuff, right? So let's pay attention here and let's find some images. All right, let's evaluate this rule at different inputs. So how about t? What's t of? And then I'm just pick a 2 by 3 matrix with real numbers in it. How about just 1, 2, 3, 4, 5, 6? Huh? Why not? Right? Just make up whatever you want. Now, according to this, I'm just replacing A1 with 1, A2 with 2, A3 with 3, A4 with 4, A5 with 5, and A6 with 6 over here for the output. So the output is, A1, which is 1, plus A2 squared, so 2 squared, minus 4 times A3, right, so minus 4 times 3. There's the constant term, plus, and then this coefficient of x is, A4 times A5, 4 times 5, minus A6 is 6, and then times x. And what are we getting here? We're getting, this is 1, plus 4 is 5, right, 2 squared, 5, and then minus 12, that'd be negative 7 for the constant term. And then the coefficient of x is 20 minus 6. 4 times 5 minus 6. 20 minus 6 is 14. So plus 14x. Right, and you see this belongs to P1, right? This is a polynomial of degree 1 or less. And there you go. All right, so we again, some terminology, we would say that negative 7 plus 14x is the image of this input, this 2 by 3 matrix here. Another thing you could say is that this matrix the 1, 2, 3, 4, 5, 6, this is one element, right? It might not be the only one. There might be more. This is one element of the pre-image of negative 7 plus 14x. And also, negative 7 plus 14x, sorry about the clutter down here, negative 7 plus 14x is in the range of this transformation. All right. You can say all these things. All right, actually it'd be pretty easy to see that, this is not the only element in the pre-image of negative 7x plus 14, because I could very easily make negative 7 plus 14x, sorry, negative 7 plus 14x. I could very easily make negative 7 plus 14x if I just have A1 be negative 7 and A6 be negative 14. So I could have, negative 7, 0, 0, 0, 0, negative 14. That 2 by 3 matrix would also have an image of negative 7 plus 14x. Or negative 7 for A1, 0 for A2, 0 for A3, and then 2 and 7, or 14 and 1 for A4 and A5, and then 0 for A6. So negative 7, 0, 0, 2, 7, 0, there's another matrix that would have this as an image. So the pre-image of an entry of an output has more, is going to have, you know, either one element or more than one element or no elements. Right? You just be careful. Don't just automatically say this is the only thing in the pre-image of -7 plus 14x. Okay, but again, hopefully you understand what's going on. Right? Inputs from some vector space, the outputs from some vector space, and pay attention to how to make the output. Right? Just look at the rule. It's just like any other like function from back in algebra class or pre-algebra or calculus. You know. All right, so just one more here. So what's T of? And again, my input is some 2 by 3 matrix. Let's go 0, -1, 5, 10, 4, -3. All right, we'll go back to the rule here and just pop in, you know, 0 for A1, -1 for A2, 5 for A3, 10 for A4, 4 for A5, and -3 for A6. So this constant term over here, A1, 0, plus, you know, -1 squared, which will be +1, and then -4 times A3, -4 times 5. There's the constant term, plus, and then A4, 10 times A5 is 4, 10 times 4 there, then minus -3 times x. You know. So we have over here 0 plus 1 minus 20, that's -19 for the constant term. And then 40 plus 3, 43, 43x for the linear term. Right? And there we go. Here's the value of this transformation at this input. Right? So again, I'm not going to write these this time. I'll just say, you know, so -19 plus 43x is the image of this 2 by 3 matrix. And this 2 by 3 matrix is in the pre-image of -19 plus 43x. And again, it's not the only matrix that would give me this, but it is one of them. And also -19 plus 43x is in the domain of this transformation here. Great. All right, I got just one more example. And then in the video following this, we're going to talk about, well, when is a general transformation a linear transformation, right? That was another concept that came up in the discussion of transformations between Euclidean spaces, right? When is a transformation a linear transformation or a matrix transformation, right? They're one and the same, and we'll see the same happening with general transformations as well in an upcoming video. All right, so here I have a transformation, a rule from, you know, taking inputs from R3, right? Vectors with 3 components. That's a Euclidean space. And my outputs are in that set of that vector space of 2 by 2 matrices, right, under standard operations with real entries. So here's the rule. T of, you know, my input is again from R3, 3 components x, y, z, equals this 2 by 2 matrix with real entries, where this is first row, first column x, first row, second column y times z, second row, first column x squared minus y squared, and the second row, second column is always 0. Okay. So again, I'm just going to do one of these, all right? As I think I'm hoping you're getting this by now, but let's just evaluate. Let's find, how about T of, I don't know, just taking any vector from R3 here. How about -2, 5, and 3? Right? How about that vector from R3? So I'm replacing, it's going through the rule here, just like any function really, right? We're going through the rule and replacing x with -2, y with 5, and z with 3. So the output, right, is going to be again a 2 by 2 matrix. That's your codomain, the set of 2 by 2 matrices. So that first row, first column is x. X is -2. Then y times z, so 5 times 3 for that first row, second column. Second row, first column, x squared, so -2 squared minus y squared, and then always 0 for that second row, second column. And then I simplify this stuff, right? So -2, then 5 times 3, 15. That's 4 minus 25, that'd be -21. Right, 4 minus 25, and then 0. And there you go. There's the output. This 2 by 2 matrix is the image of this vector. And this vector is one of the elements in the pre-image of this 2 by 2 matrix. And this 2 by 2 matrix is in the range of this transformation T. You can say all the same things every time. So hopefully this seems easy enough, right? It's just a lot of replacing your input variables with numbers or specific values, and then finding the outputs and making sure the outputs are in the correct form, right? If my codomain is a set of 2 by 2 matrices, my output had better be a 2 by 2 matrix. If my codomain is, P3, my output had better be a polynomial of degree 3 or less, right? So just pay attention to the domain and the codomain and know that my vectors from the domain have to have a certain look, and my vectors from the codomain, my outputs, have to have a certain look as well. Just make sure they have those proper looks. Alright, so I hope you enjoy problems like that, practicing evaluating transformations, and thank you very much for watching.